Now let's answer question number 4. It is on fluids and electrostatic. We have 2-point charges, 4 microcoulomb and 16 microcoulomb. Both of them are positive charges, and they are fixed at a distance of 30 centimeters apart. So let me quickly sketch that. So we have a positive charge here. We have another positive charge here. This one is, let me call this one Q1, which is the 4 microcoulomb. And let me call this one the 16 microcoulomb, which is Q2 in this case. Both of them are 30 centimeters apart. So the distance from here to here is 30 centimeters. They are apart in a vacuum. At what distance from the plus 4 microcoulomb charge along the line joining them will the net electric field intensity be zero? So here's what happens. Whenever you have charges like this, point charges, isolated charges of this sort, they can actually have electric field intensity around them. In fact, they have intensity around them. But for now, I want to restrict it to right and left. So on this right, on the right of the 4 microcoulomb, as you begin to move away, you have electric field intensity right from this point to this point to this point. On its left as well, you have electric field intensity. The same thing with this 16 microcoulomb. To the left and to the right, you have electric field intensity due to that charge, due to the presence of that charge. But when you have more than one in a system, like this now, you have 2-point charges here now. These two will contribute to the charges that surrounds them, and sorry, the electric field intensity that surrounds them. And at different position, they contribute differently. So this is what happened. At a point, these two guys can actually have their electric field intensity cancelled out. But here's one thing I want to quickly call your attention to. When we have positive charges, anything in between them, because they repel each other, their electric field intensity always cancel out based on the principle of superposition. There will always be difference in electric field intensity. So whatever the electric field intensity of this guy is at a point here, by the way, they want us to find at what distance from this 4 microcoulomb charge. Let's call that distance, let's call it R. If the total distance is 30 centimeters, that means that the remaining thing that we have here is going to be 30 minus R. So back to this now. Positive and positive charge, or any charges that are the same, if it was negative here as well, anything in between them will cancel out because of repulsion. Their electric field intensity cancels out. But if they are of different signs, like let's say we have a positive and we have a negative charge here. So what's going to happen to them is that these two are going to attract. So anything between them is an electric field intensity that will add up. But if let's say we are considering a point beyond one of them, at least both of them like this now, in this situation, these two guys will add up. Their electric field intensity will add up at this point. Same thing with this guy too. Their electric field intensity will add up here. But for this guy, when you go beyond any of them, you have their electric field intensity canceling out. That is, they are subtracting each other. But for this case now, this particular question, we're going to be using the subtraction because they are in between each other, and because of repulsion we'll have a reducing net electric field intensity. So that's very easy. We know that E is KQ divided by R squared. So in this case, we just need their electric field intensity to be the same. If they are the same, when they subtract from each other, they will be equal to 0. So that implies that we can have KQ, that is times 4 in this case, divided by R squared, will be equal to K multiplied by the Q now is 16 divided by 30 minus R squared, since that is the distance that we have here now. So K is going to cancel out. And then we have 4, we have another 4 here. So basically we have that 4R squared equals 30 minus R squared. It's a good thing we can easily find, these are perfect squares, so we can easily find the square root of this guy. So if you find the square root of this, that will be 2R, and if you find the square root of this, that will be 30 minus R. So when you solve for R in this place, you take R to this place, you have 3R equals 30. So that implies that R will be equal to 10 centimeters. R is going to be equal to 10 centimeters. By the way, I did not bother converting 30 centimeters to meters here because I'm actually doing a kind of comparison. So the whole thing kind of ratio out. So the correct answer to this is 10 centimeters. By the way, if you need full lecture on how to actually understand electric field intensity and so many things that surround electrostatic all together, just go to my YouTube. My YouTube username is being displayed right. Yeah, this is my username across all social media. You will always see there. And try to follow Pi Scholars Academy as well on all our social media. You see so many videos that I've created for this guy as well. Don't forget, if you're watching this on YouTube, don't forget to subscribe. And if you're watching this on TikTok, like, comment, and follow. I'll see you in the next one.